Hello everyone and welcome to a new lecture about probability and statistics in Python. Today we are diving into the fascinating world of normal distribution, also known as Gaussian distribution. We will study the principles with several examples and we will code all of them in Python. So let's move forward to understand the key characteristics of Gaussian distribution. Normal distribution or Gaussian distribution is a kind of continuous probability distribution, and it has a bell-shaped curve. As you can see here, the shape of this function is like a bell. It is symmetric about its mean. You can see here, this is the mean. And all type of normal distribution are symmetric. It means right side is exactly equal to the left side. And in here, mean, median, and mode all are equal. Mean is the average of a set of numbers. Median is the middle value in an ordered data set, and mode is the most frequent occurring value in a data set. So in the case of normal distribution, mean, median, and mode all are the same. The peak of the curve occurs at mu here. It means it is a unimodal. The unimodal means the distribution has only one single peak which occurs at the mean. So if we have bimodal, it will be something like this. So if our data are something like this, then we say this is a bimodal, right? But in this case, it is unimodal, and it means we have only one peak, and this single peak occurs at mean. The tails of this distribution are asymptotic. It means they approach but never touch the x-axis. They come close to zero, but they never become a zero. This distribution is fully defined by its mu and standard deviation. The total area under this curve is 1. It means 100% probability. And the inflection points occurs at mu plus minus sigma. These inflection points are the points on a curve where the curvature changes the direction. You can see here. So this one, some changes here, right? Some changes here, some changes here. So we have here one empirical rule. Empirical rule says 68% of data are within mu plus minus 1 sigma. So this one is mu plus 1 sigma. This one is mu minus 1 sigma, and 68.3 of our data are in here. Then we have this one is mu plus 2 sigma, and this one is mu minus 2 sigma, and 95.5% of data are here. You can see, and this one is mu plus 3 sigma, and this one is mu minus 3 sigma, and 99.7% of data are located in this area. This is called as empirical rule. This rule is why the normal distribution is so powerful for modeling real-world data, especially in natural phenomena and due to the Central Limit Theorem, which we will explore next. Why the normal distribution is so prevalent? Thanks to the Central Limit Theorem. The theorem says that the sum or mean of many independent and identical distributed random variables, regardless of their original distribution, approximate to normal distribution as n or sample size approaches infinity. What is the meaning of IID? Independent and identically distributed random variables are a sequence of random variables that they have the same probability distribution and they are mutually statistically independent. It means each variable outcome does not influence the other one. For a distribution with mean mu and variance sigma squared, the sample mean becomes normally distributed and n grows. This is the sample mean, and as you know, sample mean is 1 by n sum of xi. So if we increase the number of samples, then the sample mean follows a normal distribution with mu and sigma 2 divided by n. For example, you roll a 6-sided die many times. The individual roll here are 1, 2, 3, 4, 5, and 6, and the probability is 1 by 6. It's a uniform distribution, not a bell shape. But if we take sample of 50 rows each and calculate the average of each sample, so if you repeat this process many times and plot the sample average, then the CLT states that this average will form a bell-shaped normal distribution. It will be something like this, and with the mean of 3.5. So this is the average. It means most sample average might cluster around 3.5. This is the expected average of a die, and with fewer average far from the above or below. This resembles a normal curve as the sample size, like 50 rows, is large enough. Here, we formally define the normal distribution. Normal distribution is a probability distribution characterized by its bell-shaped curve governed by mean and sigma standard deviation. For example, heights, weights, and other physical characteristics. The PDF is fx with the parameters of mu and sigma is equal to 1 divided by root square of 2 pi. Pi is 314, sigma standard deviation e 2.71828 in power of x minus mu average divided by 2 sigma square variance, right? And absolutely, this one is greater than 0, greater than or equal, and x is between minus infinity to infinity. The ex, the expected value of this one, is always equal to mu, and vx is equal to sigma square. So the parameters are mean and the standard deviation. We can see three different normal distribution. This is with mean of 80 and a standard deviation of 15. This one is with the mean of 100 and the standard deviation of 5. And this is mean, and here is mean plus sigma, and here is mu minus sigma, right? So the mean is a location parameter because changing the value of mean rigidly shifts the density curve to one side or the other. But sigma is a scale parameter because if we change the value of sigma, it may stretch or compress the curve horizontally without changing the basic shape. So this one, you can see sigma a bit higher compared to this one. This is 5, it's compressed, and this is stretched. So let's move to Python to plot some of normal distribution to better understand how it works. So we want to plot some normal distribution. So for that one, we need to import numpy as np. We need to import matplotlib py plot as pl. And also in scipy, we have norm. So we will import it scipy.stats import norm. That's all. X is equal to np.len space of -6 to 6, and we will generate 100 numbers. Then in here, we go for plt.plot, and in here we will get x, and for the y values, we go for norm.pdf of x, and mu is equal to 0 and sigma is equal to 1. Then we label it as a standard normal with mu is equal to 0 and sigma is equal to 1, right? So here we go. This is normal distribution. So let's add grid as well. plt.grid. Mean is 0 and sigma is equal to 1. Now I want to add another one here. And I change this one, this standard deviation to 0.5. And I change this one to narrow, and mu is equal to 0 and sigma is equal to 0.5. You can see here it becomes compressed and more narrower. So still mean is equal to 0, but sigma is 0.5. So one more, I add mu is equal to 1 and sigma is equal to 1. So just mu is equal to 1 and sigma is equal to 1. So you can see here this green one is mu is equal to 1. You can see here mu is equal to 1, and also sigma is equal to 1. And the last one, mu is equal to -2 and sigma is 1.5. Mu is equal to -2 and this sigma is equal to 1.5. You can see this red one, so this is -2 and sigma is 1.5. So let's add the legend, plt.legend So you can see this blue color is standard, this orange one is 0 and 0.5, green is 1 and 1, and red is mu is -2 and sigma 1.5. So in here, you have seen that we calculated the PDF using this function in SciPy. Here, I want to implement the PDF. So we will go for this part as the coefficient and this part as the exponent. Def normal PDF, and in here we will get x. By default, mu is equal to 0. Later we can change it. And by default, sigma is equal to 1, and later we can change it as well. In here, we have two parts, coefficient that, 1 divided by root square of 2 pi sigma, and exponent is this part, right? So coefficient is equal to 1 divided by sigma multiply np skew RT of 2 multiply np dot pi. So this is the normalization constant. Then we have exponent. The exponent is equal to, we go for this form, 0.5 multiply x minus mu divided by sigma in power of 2. Then here we need to return coefficient multiply the np.exp of exponent. That's all. Now we generate some x values. X values are np space of from -3 to 3, and we generate 10 numbers. Then here we can print normal underscore PDF, and we add x values here, right? So these are the values that we have generated. If we want to compare whether this function is okay or not, we can compare using the SciPy function, right? So print, this time we go for norm.pdf of x values. So you can see almost the same, right? It means this function is correct. Now we want to check the standard normal distribution. The standard normal distribution is a special kind of normal distribution where mu is equal to 0 and sigma is equal to 1. We show it by z, standard normal random variable. Probability density function of z is equal to, because in here, this mu is equal to 0, right? And this sigma is equal to 1, and this sigma is equal to 1. So we don't have this one, we don't have this one, we don't have this one, right? So we have 1 by root square of 2 pi e in power of minus z squared divided by 2, and z is from minus infinity to infinity. Again, this one produces a bell-shaped curve. The CDF of z score is probability of z less than or equal to a given z is integral of minus infinity to z, and this part come here. We show the CDF by phi z, that is probability of z less than or equal to a given z, integral of minus infinity to z 1 by root square of 2 pi e in power of minus t squared divided by t dt. Let's dive into a practical example. We're going to calculate standard normal probabilities. For example, z less than or equal to 1.25 and z greater than 1.25. So we show the probability of z less than or equal to 1.25 using phi 1.25, right? And this one equals integral of minus infinity to 1.25 1 by root square of 2 pi e in power of minus t squared divided by t dt. Calculation of this integral is not easy. That's why, for simplicity, there is one table that is called as z table or standard normal distribution table. And this standard distribution normal table helps us to find the result of that integral. You don't need to calculate this integral again and again. This table provides the cumulative probability or area under the curve to the left side. So if this point is 1.25, so we can find the area here, right, in this table, where mean is equal to 0 and standard deviation is 1 for standard normal distribution. This table is organized with rows, and these rows representing from this is a portion of that table, minus 3.4 to 3.4, for example. And in the rows, you can see the integer part dot 1 decimal point. And in here, you can see up to 2 decimal points. For example, I want to find the value for 1.25. So I will go and find 1.2 here and 0.05 here. So I will come to this value, right? So the area is equal to 0.8944. It means the area of this shaded area is 0.8944. Now, I want to find out probability of z greater than 1.25. This one is 1 minus probability of z less than or equal to 1.25. It means 1 minus this value, right? So 1 minus 0.8944 is equal to 0.1056. So this area, the area of this shaded area is this value. For example, we want to find the probability of z less than 1.25, right? So def z table, in here we will get z. So in here we will receive z, and also we will receive another parameter, that is, we call it as, for example, c. If c is true, right, it will return probability of z less than or equal to z. It means cumulative. Otherwise, probability of z greater than a given z. So you say c is equal to true. Then here, if c is true, return norm dot CDF of z, right? Otherwise, return norm of 1 minus CDF, survival function, SF of z. That's all. Print P of z less than or equal to 1.25. This is equal to z table, and we will pass 1.25 because it is less than or equal to 1.25. We don't need to we don't need to pass the c. So here I missed the comma. So it is 8943. Then we will do the same. This time we go for z greater than 1.25, and in here we need to pass false, but it is the other side, so it is 1.5. And for between, right, so if I want to go for print z between minus 1.25 up to 1.25, this equals to z table 1.25 minus z table of minus 1.25, based on that equation that we have 0.788. Now it's the proper time to touch the z-scores. So we use the z-scores for probability calculation. A z-score standardize any normal random variable. So if you have any kind of normal random variable, you can standardize it using z-score. How? By measuring how many standard deviation it is from the mean. Equation is z is equal to x minus mu divided by sigma. So you can standardize any normal random variable using this formula. Then we go for z table that you have seen here. This provides the CDF value for z-scores, allowing us to compute the probability of z less than or equal to z or phi of z. Probability of z less than or equal to z is CDF or phi of z. Probability of z greater than z is 1 minus phi of z. And the probability of z between a and b is phi of b minus phi a. Once again, a z-score shows how far a value is from the average in a normal distribution, and we measure this one in standard deviation. Then we can go to the z table to find the probabilities. For example, we have a population with mu 50 and sigma 10. Find the probability of x bar, this sample mean, less than or equal to 51 if the number of sample is 64. So first we will go for standard error. This standard error is sigma divided by root square of n, which is equal to 10 by root square of 64 is equal to 10 by 8 is equal to 1.25. In here, why we calculate the standard error? Because here it says x bar, it means sample mean, right? So we need to go for a standard error. The standard error measures the variability of the sample mean across different samples from the sample population. That's why we go for sigma divided by root square of n. Then in this case, for the z score, we go for x bar minus mu divided by standard error, which is equal to x bar minus mu divided by sigma divided by root square of n. This is because we are dealing with the distribution of sample mean. So if it was not sample mean, we go for sigma. it will be equal to, what is the sample mean? 51 minus 50 divided by 1.25, which is equal to 0.8. Probability of z less than or equal to 0.8. So for this one, we need to go for the table, right? 0.8, z less than 0.8. So 0.8 is here, right? Because 0.8, we can write 0.8 in this form, right? 0.800, right? So here, 7881. So it will be 0.7881. And the probability of x bar 51 is equal to approximately 7.881, or you can say 78.81%. Now it's the time to learn the critical values. Critical values are specific z-scores on normal distribution curve that mark the boundaries of certain percentage. For example, 90%, 95%, etc. These help us to find probabilities or make decisions in statistics. We denote them as Z alpha, which these are the points where the area to the right under the standard normal curve is equal to alpha. So if this point is Z alpha, then the area here is equal to alpha. So probability of Z greater than or equal to Z alpha is alpha. Or you can say here the tail area. Also, we can call this one the Z alpha, as the Z alpha is the same as 100, 1 minus alphath percentile, right? So this table lists the most useful Z percentiles and Z alpha values. So for example, if alpha is 0.1, it means it is 19th percentile, and Z of 0.1 is equal to 1.28. If alpha is 0.05, this means 95th percentile, and the value for Z of 0.05 is this one. So you can see the rest is here. Later, we will use them a lot. These values are crucial for hypothesis testing and confidence intervals. Later, we will study them in details. Let's see an example how to use critical values. If alpha is equal to 0.05, it means 100 multiply 1 minus 0.05, it means 95th percentile of the standard deviation. It means Z of 0.05 is the 95th percentile of the standard distribution, and it means the phi of Z 0.05 is equal to 0.95, right? And the value for this one is 1.64. How? Based on this table, right? For 95, we have 1.645. If we consider this point here as 1.645, then the area under this part is 0.05. Also, 5% of data is here. So 5% of data here and 5% of data here. And this area is between them is 90% of the area. 90% probability, or 90% of data is between minus 1.645 and 1.645. We have a new terminology, percent point function, or PPF. This is simply the inverse of CDF, or quantile function. We call it as PPF or quantile function. If you have a probability like P between 0 and 1, that the PPF returns the value of X such that the probability of X less than or equal to X is equal to P. It's the other side, right? So PPF of P is equal to X, CDF of X is P. So the other side of CDF is PPF. And for a standard normal distribution where mu is equal to 0 and sigma is equal to 1, PPF is phi inverse or CDF inverse of P. For example, if you have a question like below what value do 95% of the observation falls, we can go for PPF. Now I want to plot the PPF. So for PPF, P is equal to NP diagonal space of 0.001 up to 0.999, and I will get 100 to avoid 0 and 1. Then PPF values are norm.ppf of p values. Then I will plot it. So plt.plot p and ppf values, and color should be like blue, and label it as ppf. So here we go. This is the line plt.grid. Okay, so this is the plot for ppf. Example here, two examples we will see. One is for standard normal distribution where mu is equal to 0 and sigma is equal to 1, and another one for general normal distribution. For example, find 95th percentile, right? So we go for ppf of 0.95 is equal to what? So for this one, we need to go to the table and find 0.95, right? So we need to go and here and find 0.95. So it will be something like here, right? So it will be something like 1.645. And another one is for general distribution. So in this case, we say x is equal to mu plus sigma multiply ppf. This example is about IQ scores. And for example, IQ score can be like less than 85, greater than 130. So we want to practice with this example. If you have mu of 100 and sigma of 15 for one example, find the 90th percentile, right? So in this case, x is equal to 100 plus 15 plus ppf of 0.90, which is equal to 100 plus 15 multiply. Again, for this one, we will go through table, something here. So it will be 1.28. 1.28 will be something like 119.22. We have already defined a standard normal distribution where mu is equal to 0 and sigma is equal to 1. Simply, non-standard normal distribution is where mu is not equal to 0 and sigma not equal to 1. So to work efficiently with non-standard normal distribution, we standardize them using this equation of z-score. Z is equal to x minus mu divided by sigma. Then probabilities for x are computed using the standard normal of probability of x less than or equal to x is phi of x minus mu divided by sigma. The empirical rule still applies here. So for any normal distribution like 68%, 95%, and 99.7%, of data lies between 1 standard deviation, 2 standard deviation, and 3 standard deviation. It means mu plus 2 standard deviation, and mu plus 3 standard deviation. We have x as a random variable which follows mu is equal to 100 and sigma is equal to 15, right? We want to find out the probability of x less than or equal to 115, right? So in this case, z is equal to 115 minus 100 divided by 15 is equal to 1. Then probability of x less than or equal to 115 is equal to phi of 1, which is equal to phi of 1 is equal to 8413. 0.8413. Then we go and find the probability of x less than or equal to p, right? If you want to find out the probability of x less than or equal to x, for this one, we find z such that phi of z is equal to probability of z is equal to phi inverse of p. Right? So we need to find P in the table, then we find the corresponding row number and column number. Then we will convert using this equation that we have already, x is equal to mu plus z sigma. For example, I want to find 90th percentile here. So in this case, Q inverse of 0.9 is equal to, so it means I go to the table and I find 0.9 here. So it will be something like here, 1.28. So it will be 1.2816, right? I will show you how to find using Python as well. Then x is equal to 100 plus this value 1.2816 multiply 15, which is equal to 119.22. This is the 19th percentile, right? I want to find out 95th percentile as well. So in this case, phi inverse of 0.95 is equal to this one, 1.64, then 100 plus 1.64 multiply 15, which is equal to 124.67. It means this is the critical value for 95th percent. For example, mu is equal to 100 and sigma is equal to 15, right? Then I want to find out probability of 0.95. Then I go for ppf, right? So zp is equal to norm dot ppf of my p, and xp, the 95th percentile of x, is equal to mu plus z underscore p multiply sigma, based on the equation that we had. So we can print that 95th percentile of n of 115 square is equal to x underscore p with 2 decimal points. So it is 124.67. I want to find probability of IQ greater than 130, right? So in here, I go for Z1 is equal to 130 as the x minus mu divided by sigma, right? And here, P1 is equal to norm 1 minus CDF, or survival function of Z1. So let's print it. Print f probability of IQ greater than 130 is equal to P1 by 4f, or we can print it in percentage. So you can say P1 multiply 100, right? Okay, so 2.28%. Find probability that IQ is between 85 and 115, right? 115. So here, so lower bound and upper bound. Lower bound is 85, upper bound is 115. So lower bound is equal to x85 minus mu divided by sigma, right? And also z high is equal to 115 minus mu divided by sigma. And then P2 here, this probability is equal to norm.cdf of z high minus norm.cdf of z low. We can print it in the same way here. Probability of z between 85 and 115 is P2, or P2 in percentage, which is 68.27%. I want to find 19th percentile. So Z of 90 is equal to norm dot ppf of 9.9, right? So in this time, we find those corresponding row number and column number, right? So in here, we find phi. It means we have row number and column number. We want to find value. In here, we have the value and we want to find row number. And so then IQ 90 is equal to mu plus Z of 90 multiply sigma. Okay, now we can print it. Print correct. So 119.2. And the same thing, we can go for 95. We can do the same thing for 95. And this is 124.67. So this is the proposition. If x has a normal distribution with mu, then z is equal to x minus mu divided by sigma. Now we want to go for normalization, standardization. This is a non-standard, and this is an standard, right? So we want to convert this one. So in here, our random variable follows a normal distribution with mu and sigma square. But in here, our mu is equal to 0 and sigma is equal to 1. It means this is a standard, right? So in this case, just we will convert mu to 0, and we will calculate all the values using this equation of z squared, x minus mu divided by sigma. So then the probability of x between a and b is the probability of, instead of a, here we will bring this equation. So instead of x, a minus mu divided by sigma, and b minus mu divided by sigma. Based on this equation that we had here already, based on this equation, probability of z between this one and this one is phi of b, this is phi of b, minus phi of a, right? This is phi of a. And probability of x less than or equal to a is phi of a minus mu divided by sigma, and probability of x greater than b is 1 minus this one, which is also known as CDF. Here, we extend critical values to non-standard normal distribution as well. For a normal distribution with mean of mu and a standard deviation of sigma, the critical values for 19th percentile is alpha is 0.1, and you can say that z of alpha is 128 based on the table that we have. If you have alpha is equal to 0.05, it means 95th percentile, and z alpha is 1.645. For 97.5, alpha is 0.025, and z of alpha is 1.96. The same for this one. So if we have any x random variable which follows a normal distribution with the mean of mu variance of sigma squared, then xp is equal to mu plus zp multiplied sigma. Here we're gonna see a proposition for finding percentiles of any normal distribution. For the pth percentile, we compute x is equal to mu plus zp multiplied sigma, and this zp here is the pth percentile of a standard normal distribution. This generalizes our earlier examples and is crucial for application like setting threshold or confidence interval. So the 100th percentile of normal distribution, which has a mean of mu and a standard deviation of sigma, is easily related to 100th percentile of the standard normal distribution, and we calculate like mu, and this is the zp, and this is the sigma. Another way of saying this is that if z is the desired percentile for a standard normal distribution, then the desired percentile for normal of mu and sigma distribution is z standard deviation from mu. Here we explore how the normal distribution approximates the binomial distribution under certain conditions. So you remember that mean value and the standard deviation for binomial distribution was E of x was equal to np, and sigma x was equal to root square of npq, where q was equal to 1 minus p. So here we can see the binomial probability histogram for binomial distribution with n is equal to 25. Probability of 6 is equal to 0.6. So mu is, based on this equation, n multiply p is equal to 15, and standard deviation is n, and this is p, and this is q as 1 minus 0.6, so 2.449. In here, we are going to approximate the binomial distribution using normal distribution. It is reasonable. Why? Because there are some conditions. The condition says n multiply p should be greater than 5, right? So we have n multiply p is 15. That's why this one is okay. And n multiply 1 minus p or q should be greater than 5. Then this one is okay. So the normal approximation is valid here. In here, we have a histogram of binomial distribution. We have approximated this one using this blue curve, that is the normal distribution. If x is a binomial random variable with n trial 6's probability, and 6's probability is like p, and if the histogram is 2 squared, then x is approximately normal distribution, and in here mu will be is equal to np, and sigma is root square of npq. This one should be q. For a specific value, like for example, probability of x is equal to k is equal to probability of y between k plus 0.5 and k minus 0.5, right? So this y is the normal random variable with the same mean and standard deviation. So we just added some, something to improve the accuracy. So probability of p less than x or equal to x of a binomial distribution or are under the normal curve to the left of x plus 5. So we add some 0.5 in order to improve the accuracy. Suppose that 25% of students at a large public university receive financial aid. X as a random variable is the number of students in a random sample of 50 who receive financial aid. And the probability is 25%. Then, based on the equation that we have, this one is n multiply p, which is 12.5, and this one is root square of npq, which is 3.06. Based on the condition, because np is equal to 12.5 and n multiply 1 minus p is equal to 37.5, so the normal distribution is valid. Now we want to find the probability of x less than or equal to 10. It's binomial of 10, 50, and 25. So for improving accuracy, we add 0.5 here. So phi of 10, instead of 10, we go for 10.5 minus 12.5 mu. This is the mu that we find here, and this is standard deviation. This one should be minus 0.65. Phi of minus 0.65 minus 65, it will be something like here, this one, right? 2578, this one is correct. Then we go for probability of x between 5 and 15. It is binomial of 15, 5, 25, and same here. So again, this one we will add 15.5, and this one we add 4.5. So if you go and find the phi of this value and this value, then we will come up with this one. So for the example of financial aid, so in here, we suppose our n is equal to 50 and probability of success is equal to 0.25, right? So here we calculate mu. Mu is equal to n multiply p. So what is mu here? Mu is 12.5. Then sigma is equal to np dot sqrt of n multiply p multiply 1 minus p. Then we can print sigma. So sigma is 3.06. Now we calculate probability of x less than or equal to 10 with continuity correction. It means 10 plus 0.5, right? Z1 is equal to 10 plus 0.5 minus mu divided by sigma. And then we can print norm dot CDF of Z1. Now I want to calculate the probability of x between 15 and 5, right? So for this one, I go for lower bound and upper bound. For the lower bound, for continuity correction, I go for 4.5 instead of 5. And for 15, I go for 15.5, right? Z lower is equal to 5 minus 0.5 minus mu divided by sigma. And Z upper is equal to 15 plus 0.5 minus mu divided by sigma. We can print this probability. Probability of this one is norm dot CDF of Z upper minus norm dot CDF of Z lower. This one should be Z upper. Okay, that's all for today. Thank you for joining me today on this exploration of the normal distribution. We have uncovered its bell-shaped elegance defined by the mean and standard deviation, and we have seen how the imperial rule like 68%, 95%, and 99.7% within 1, 2, or 3 standard deviations guides our understanding of data. The central limit theorem reveals why this distribution appears so often in nature and statistics, while the standard normal distribution and z-scores equipped us with tools to calculate probabilities and percentile. We extended these to non-standard distribution and even approximated binomial distribution, showcasing its versatility. There are some common misconceptions here. All data are not normally distribution. Many real-world data sets are not normal. Normal distribution implies causation. It's just a description of data. Outliers are impossible, just very unlikely in true normal distribution. All symmetric distributions are normal. No, many symmetric distributions are not normal. So, what are the limitations of normal distribution? It's not appropriate for all type of data, for example, bounded data or highly skewed data. They are sensitive to outliers, and also assumption of normality can lead to incorrect conclusion if violated. This foundational knowledge, easily implemented in Python, empowers us to analyze real-world phenomena from financial models to scientific experiments. I encourage you to experiment with this concept, perhaps using the scripts we have discussed, and let the normal distributions insight shape your data-driven decisions. Thank you and see you in the next lecture.